Hello, friend. I'm glad you've wandered to this quiet edge of the night. Let the noise of the day fall away like a tide pulling back from the shore, leaving only stillness and a soft sense of room to breathe. Think of this moment as a dim, peaceful nook where science leans close, speaks in a whisper, and nothing asks to be solved before sleep. This is Fall Asleep to Astronomy, and I'm here with you. Tonight, we'll drift toward a small, flickering mystery from beyond our solar system, an interstellar visitor called 3IATLAS. Some say its strange behavior carries a hint of intention, a faint suggestion that it might not be just another piece of wandering rock. Avi Loeb has spent years following those clues, letting the data glow softly under careful eyes. We'll cradle that idea gently, turning it only enough to see the shimmer without waking the mind too sharply. And if these quiet explorations ease you into rest, a soft like and a gentle subscribe help other sleepy travelers find their way here without disturbing the calm. When you're ready, let the night settle around you. We'll step into the story together, unhurried and warm. There are a few dates that sit quietly in this story, like small circles on a calendar pinned to the wall of the night. One of them is November 19th. On that day, NASA finally shared a set of images they had been holding for weeks, light gathered by a whole fleet of spacecraft, watching 3IATLAS as it slipped around the Sunday. For about 45 minutes, they spoke in careful, steady voices, repeating that this visitor is a comet, just a comet, a ball of ice and dust from another star system, behaving much like the comets we already know. But if you look closely, the images they released seem to whisper something a little stranger than the words that accompanied them. Another date comes and settles right next to the first, November 20th, just one day later. While the official message was still drifting through news feeds and headlines, a few patient amateur astronomers were out under their own dark skies, collecting their own photons. They pointed their telescopes at the same little streak of light, took many long exposures, and then stacked those images together, the way you lay thin sheets of tracing paper on top of each other until a hidden line begins to appear. In the combined glow, something unexpected came into focus. Instead of a simple fuzzy head with a tail streaming away from the sun, they saw an X. Two thin, sharp jets of light crossed each other, shooting sideways from the comet, not along the usual direction of sunlight, but almost at right angles to it. Each of those narrow lines stretched for about 1 million kilometers. It's a number so big, it resists feeling real. So the mind reaches for comparison. That's more than twice the distance from Earth to the Moon. If you could lay one of those jets down between us and our satellite, the line would pass the Moon and keep going, still straight, still clean. Then another quiet detail joins the picture. If those jets began forming near October 29th, when 3IATLAS passed closest to the Sun, at a point we call perihelion, then the material or objects that trace those lines must have been moving at around 500 meters per second for about 22 days. No obvious wobbling, no slow curve, just a steady, long-lived motion. Avi Loeb looks at those numbers and lets a simple question rise. If these are trails, what is leaving them behind? Are they just fragments of ice and dust thrown off naturally near the sun? Or are they something that can quietly hold a course and speed more faithfully than fragile ice usually can? While that question hangs in the background, another date waits further ahead, December 19th, the day when 3IATLAS will pass closest to Earth. It sits there on the calendar like a soft marker, a time when our view will sharpen and some of this uncertainty might grow clearer or stranger. But even before that, the sense of oddness had already been building. For 41 days, people who follow this little visitor had been waiting in a kind of suspended curiosity. It had been 41 days since 3IATLAS slipped behind the sun from our point of view and emerged on the other side, changed, showing multiple jets pointing in directions that do not quite match what we expect from comet physics. It had also been 41 days since it swept through perihelion at about 203 million kilometers from the sun, close enough that the heat should have driven its ices to behave in familiar, mostly symmetric ways. During those same 41 days, NASA was unusually quiet. There was an earthly reason for that. A government shutdown had begun on October 1st, just as the comet was entering the most revealing part of its journey through the inner solar system. The big systems stayed awake. The deep space network kept listening. The spacecraft kept collecting data, but public updates slowed to a weak trickle. Briefings were delayed, websites stayed still, and into that silence drifted speculation, theories, and the faint, uneasy feeling that important pieces of the story were being held back. When November 19th arrived, it came with a carefully prepared press conference, like a vault door finally swinging open. NASA laid out a mosaic of views from 15 different spacecraft, each catching 3IATLAS from its own angle. The Mars Reconnaissance Orbiter, circling the red planet, had taken one of the closest looks on October 2nd, when the comet was only about 19 million miles from Mars. Its powerful camera recorded a smeared streak of light, blurred by the motion of both spacecraft and comet over a short exposure. Even so, the smudge was not featureless. Other missions added their own pieces to the puzzle. Maven traced the hydrogen cloud, the coma of gas and dust surrounding the nucleus, glowing softly in ultraviolet light. Lucy, on its path toward the Trojan asteroids, grabbed a look. Psyche, heading toward a metallic world, did the same. Stereo and Punch sent in their perspectives from different locations in the inner solar system. Together, all these views created a gentle, multi-eyed portrait of an interstellar object warming up near a star for the first time in a very long time. Over this rich tapestry of data, the spoken message stayed simple and firm. Again and again, officials repeated that 3IATLAS looks and behaves like a comet. One administrator said it clearly. All the evidence, he insisted, points to a cometary nature, familiar physics, familiar behavior, just formed in another star system instead of our own. Another leader in NASA's science division reassured listeners that no technosignatures had been seen, nothing that would suggest anything artificial. The word comet was used so frequently that, to some ears, it began to sound less like a neutral label and more like a gentle mantra. While those words were washing over the public, Avi Loeb was watching the images themselves. He was less focused on the official narration and more on what the light was quietly sketching on the detectors. In the Mars Reconnaissance Orbiter data, blurred though it was, the halo around 3IATLAS did not look like a simple round coma with a single tail pointing away from the sunday. There was a hint of structure, an X-shaped pattern, faint but persistent, with material stretching in 4 directions, where normally there should be one main direction and perhaps a secondary feature. That shape was not entirely new. Amateur astronomers had already seen the ghost of that X in August and September, before the comet disappeared behind the sunday. Their equipment is humbler, but their care is deep, and their earlier images had shown something similar, just at the edge of visibility. Now, seeing the same pattern from a spacecraft orbiting Mars, far removed from Earth's own satellites and clutter. It became harder to dismiss the X as a simple artifact or a trick of the eye. During the press event, Tom Statler, a lead scientist for small bodies in NASA's planetary division, chose to lean into the sense of wonder. He talked about how fast 3IATLAS is moving through our neighborhood, about 3 times faster than the average speed at which nearby stars circle the center of the Milky Way. He suggested that this object has likely wandered through interstellar space for a very long time, perhaps having been thrown from a planetary system older than our own. The idea carries its own quiet chill, a shard from another sun's family, formed before our sun even existed, now drifting past us in the dark. He called it a window into a deep past that predates Earth and the sun themselves. Beautiful words, the kind that invite the mind to stretch. But there were also things he did not say. He did not address the X pattern. He did not explain why there seemed to be 4 directions of material ejection instead of 1 or 2. He did not discuss what kind of mass loss could feed those long, sharp jets. It's not that he was hiding anything. It may simply be that there were no clear answers to give. The mystery was acknowledged in tone, but not yet resolved in substance. The very next day, November 20th, the image from the amateurs made that mystery harder to stay away from. Michael Yeager, Gerald Riemann, and Enrico Prosperi had been tracking 3IATLAS since it emerged from behind the sun in early November. That night, they took 20 exposures, each one about 100 seconds long, and added them together with care. Stacking images like that is a bit like listening to the same soft sentence again and again until the noise falls away and the words become clear. When they were finished, the X was no longer a hint. It was unmistakable. 2 narrow jets cut across the usual sun-aligned features, like bright threads embroidered over a faint, normal tail. One stretched up in their image, the other down, each reaching to around 1,000,000 kilometers from the nucleus. They were strikingly straight and well-defined. Comets can have jets. That part is not strange. As an icy body warms near the sun, frozen gases turn directly to vapor, carrying dust with them, and creating visible streams that can even push the comet slightly off its purely gravitational path. This is well-tested science. But in our usual understanding, those jets respect the geometry of sunlight and motion. Material tends to flow away from the sun, curving gently under radiation pressure and orbital dynamics. Sometimes, perspective tricks us and creates odd-looking dust structures, like anti-tails that appear to point the wrong way, but underneath, the physics remains simple. Sideways, jets that remain arrow-straight over 1,000,000 kilometers are not part of that familiar picture, especially when the nucleus itself is known to be spinning. That rotation is a crucial piece. Observations from July and August had pinned 3IATLAS's spin period at about 16.16 hours, a result confirmed by multiple teams. If the comet is still spinning at that rate, then any jet fixed to its surface should sweep through space like water from a rotating sprinkler. Material flowing out at a typical cometary speed around 400 meters per second takes roughly a month to travel 1,000,000 kilometers. In that month, with a 16-hour spin, the comet would rotate around 45 times. Instead of a single straight beam, you would expect a series of arcs, a broad fan, or a chain of overlapping puffs, each new burst of material sprayed in a slightly different direction as the nucleus turns. The November 20th image, however, shows something much more like thin, collimated beams. They look as though whatever is tracing them isn't rotating with the nucleus in the usual way, or isn't made in the usual way at all. Faced with this, Avi Loeb laid out three broad possibilities, like three paths branching out in a quiet mental garden. The first is that the jets are entirely natural, the result of some configuration of ice, rock, and heat that we do not yet understand. If that's the case, then 3IATLAS is showing us a part of comet behavior we have never seen before, and our models of how jets form and flow will need to expand. The second is that the lines are not true jets from the nucleus at all, but trails left by fragments that separated from the main body near perihelion and are now moving along their own paths at around 500 meters per second. In that picture, these are not streams of gas from a spinning source, but the straight paths of small bodies, thrown outward in some kind of breakup or violent shedding event, each carrying its own momentum. The third possibility is the one that sits a little apart, the one that makes people lower their voices. In that scenario, the lines could be the exhaust of technological thrusters, devices that can maintain their orientation over long periods for the purpose of controlled navigation. It is a heavy thought, and Loeb treats it carefully, not as a conclusion, but as a possibility that the evidence does not yet allow him to completely dismiss. At the same time, he is careful to point out the most mundane explanation as well. The sideways streaks in the November 20th image could, in principle, be nothing more than a satellite trail, a human-made spacecraft in Earth orbit passing through the field of view, leaving a straight, bright line that just happens to intersect the comet. Astronomers are used to such intrusions. Earth's sky is busy now. But the October 2nd image from Mars makes this explanation feel less comforting. The X-like structure is present there too, faint but real, in data taken from a spacecraft millions of kilometers away from Earth, far beyond the reach of our communication satellites. If the November 20th lines were just a satellite artifact, it would be an odd coincidence for them to echo a pattern already seen from Mars orbit weeks earlier. Two very different vantage points, one repeating shape. So the question lingers, did 3IATLAS release something near perihelion? If the structures began on October 29th and now extend to 1,000,000 kilometers, the implied speed, about 500 meters per second for 22 days, does not sound like the gentle breath of sublimating ice. It sounds like objects with real momentum, things that were either flung out in a strong fragmentation event or steadily pushed by some process we do not yet recognize. To keep track of all these oddities, Loeb has been maintaining what he calls an anomaly catalog, a list of ways in which 3IATLAS refuses to fit comfortably within the patterns laid down by other comets. Each entry on its own might be explained away as a quirk of viewing angle, measurement, or natural variation, but taken together, they begin to feel like a mood rather than an accident. By November 15th, that list had grown to 12 separate items, 12 quiet marks on the page where reality does not quite line up with expectation. We have seen interstellar visitors before. Oumuamua, in 2017, arrived without any obvious cometary activity at all. No tail, no coma, just a tumbling object with a strange shape and a small, unexplained push. 2I, Borisov, in 2019, behaved like a classic comet, trailing gas and dust in a way that felt familiar and reassuring, as if to say, interstellar space makes ordinary snowballs too. 3IATLAS began its visit, looking similarly ordinary, a comfortingly normal comet from far away. But with each new image and each new measurement, it has drifted a little further from that comfort, until those 12 anomalies now sit together like a small stack of stones at the edge of a path, quiet markers, inviting anyone who passes to pause and to consider whether this is merely the strangest natural comet we have ever met, or perhaps the first clear sign that something in the dark is more deliberate than we once dared to imagine. Loeb keeps this small list the way someone might keep a worn notebook by the bedside, each page holding a detail that wouldn't quite leave him alone. None of the entries says alien. None of them proves anything. They are simply places where 3IATLAS steps a little sideways from what experience says should happen. The first thing he writes down is the path itself. 3IATLAS is on a retrograde orbit, moving opposite to the direction the planets circle the Sunday. That, by itself, is not surprising for a visitor from between the stars. Such objects can come at us from almost any direction. What raises an eyebrow is the way its orbit is tilted. The plane of its motion lies within about 5 degrees of the ecliptic, the thin, flat disk where all the major planets travel. The chance of an interstellar object just happening to skim so close to that plane is small, perhaps something like 1 in 500. Not impossible, just unlikely. On its own, that would be a curiosity and nothing more. But the ecliptic is not just any plane. It's where all the busy things in our solar system live: Earth, Mars, Jupiter, the swarm of asteroids and comets we watch most closely. If you wanted to design a flyby path that gave you a series of good looks at many worlds in one trip, you would aim your trajectory into that thin sheet. You wouldn't pass high above or deep below, where there is nothing much to see. You'd come in flat, almost exactly the way 3IATLAS has done. Another note in the notebook is about a strange anti-tail. In July and August, and again in early November, 3IATLAS showed material streaming, not away from the sun, but toward it. We do know of anti-tails in comet science. Most of them are tricks of perspective. Larger grains of dust linger along the orbit behind the comet, and from our changing viewpoint, it can look as though a tail is pointing forward. When you work out the geometry, the illusion disappears. Here, it does not. The sunward feature of 3IATLAS is not just a trick of viewpoint. It behaves like real material flowing toward the sun, apparently pushing back against the solar wind that should sweep it away. For gas and dust to do that, the outflow has to be fast and energetic, fast enough to overcome that outward pressure. That kind of persistent push requires more energy than simple sunlight on a passive, icy surface usually provides. Another line: mass and speed. The nucleus of 3IATLAS appears to be roughly 1,000,000 times more massive than Oumuamua, and about 1,000 times more massive than 2I Borisov. At the same time, it's moving faster than both. Being unusually big is one thing. Being unusually big and unusually quick at once is something else. Loeb estimates the odds of that combination as less than 1 in 1,000. Again, not impossible, but when you start stacking low probability traits on top of one another, the mind begins to wonder if it is looking at pure chance or at some quieter pattern. The timing and layout of the orbit add another entry. This object has threaded its way through the inner solar system in a way that brings it within tens of millions of kilometers of Mars, then past the far side of the Sun where Earth cannot see it at its closest approach, and later near Jupiter. It came nearest to Mars around October 3rd, at about 29 million kilometers, close enough for cameras in Mars orbit to catch it clearly. It reached perihelion on October 29th, hidden behind the Sun from Earth's view. Then we'll pass relatively near Jupiter in March 2026. At about 54 million kilometers, if you were planning a slow, surveying tour of the inner system, letting one path offer glimpses of several planets and minimizing your time in Earth's full view at closest solar approach, you might draw something very like this. Loeb's back of the envelope probability for such a geometry happening by chance is tiny, on the order of 1 in 20,000. Still not proof of design, but another small stone added to the pile. To keep himself honest, he reminds people what small probabilities really mean. Shuffle a deck of cards, and the precise order you get has a probability so minuscule it may as well be 0. Yet you still get some order. Unlikely things happen all the time. The question isn't, is this unlikely? Most specific things are. The question is whether the particular pattern of unlikely traits we see here hints at intention, or is just the natural texture of a universe where trillions of objects fly on trillions of paths. Further down the list is something that happened far from the Sun, out near Jupiter's distance. At about 6.4 astronomical units, when sunlight is weak and water ice should mostly sleep, 3IATLAS was already awake, outgassing, forming a coma, behaving like a comet much closer in. That early activity could mean that its ices are different, made of more volatile substances like carbon monoxide or carbon dioxide that evaporate more easily. We know such ices exist in comets, but the level of activity this object showed at that distance seems stronger than expected, as though either its composition is unusually rich in these volatiles, or something inside it is adding extra heat. Then there is the way it has stubbornly stayed in one piece. Comets are fragile things. As they warm, their surfaces crack, gases burst out, loosely bound chunks can tear away. Some break into several pieces, some fall apart entirely. 2I. Borisov surprised people by staying intact, but that was still within the range of what we've seen. 3IATLAS has now passed within about 1.44 astronomical units of the Sunday. It has clearly undergone strong outgassing, evidenced by its many jets, and yet images from mid-November show a single, coherent nucleus with no sign of major breakup. Staying whole under that kind of stress suggests either an unusually strong internal structure or a very different internal makeup than the rubble pile comets we're used to. It is as if the core of this thing is held together more tightly than the standard snowball of dust and ice. The way its brightness has changed with time adds another line. Normally, as a comet approaches the Sun, its brightness follows a fairly simple rule, a power law that depends on its distance. Most comets brighten with an exponent between about -2 and -3. 3IATLAS brightened more steeply, with an exponent closer to -3.9, flaring up more strongly than expected as it came inward. After perihelion, instead of fading in step with its increasing distance from the Sun, its brightening curve flattened and it continued to grow brighter for a while. That implies sustained, or even increased, activity after its closest approach, a behavior that is not the norm. Spectroscopic observations added another quiet oddity. The gases around 3IATLAS include familiar components: carbon dioxide, water, carbon monoxide, carbonyl sulfide. Nothing shocking there, but the ratio of dust to gas appears to be lower than in typical comets. In other words, this object seems relatively gas-rich and dust-poor. That matters because gas-rich comets tend to be more sensitive. Small changes in sunlight can trigger large changes in activity, making their behavior more dramatic and harder to predict. Some observations have also hinted at the presence of nickel in the material shed by 3IATLAS. Nickel does exist in comets, but usually only in tiny amounts. If this detection holds up, it suggests that the object either formed in an environment with different chemical richness than our solar system, or that its material was processed under conditions that are not quite like those that shaped our usual comets. That would fit with an interstellar origin, but it still adds another distinct note to its spectrum. Then there is the way its path has deviated slightly from what gravity alone would dictate. As 3I-ATLAS approached perihelion, its orbit showed a small but measurable non-gravitational acceleration. This, too, is not surprising by itself. When comets outgas, the escaping material acts like thrusters, pushing the nucleus a little and altering its trajectory. But for that push to match what we observe, the directions and strengths of the jets have to add up in a way that agrees with the light we see. Here the picture gets tangled. After perihelion, the jets of 3I-ATLAS seem to point in several different directions at once, some toward the sun, some away, some almost sideways. For the overall acceleration to fit the data, those various thrusts must blend into a net push that matches the orbit. Loeb's calculations suggest that this would require a very large fraction of the comet's initial mass, more than 10 to 20%, to be ejected near perihelion. That is a huge amount of material to lose without the nucleus visibly breaking apart. The anti-tail refuses to go away as well. The sunward structure that first appeared in July kept showing up through November, not as a faint curiosity but as a strong, persistent feature. Images from mid-November show a bright anti-tail alongside more ordinary, sun-aligned tails, 3 distinct directions of outflow at once. To explain such a long-lived anti-tail, one idea is that 3I-ATLAS is releasing unusually large dust grains, with sizes around 100 micrometers, much bigger and more massive than the fine dust that usually dominates comet tails. Grains that big would have enough momentum to plow through the solar wind and keep moving sunward for a long time, giving the appearance of a forward-pointing tail. But producing vast quantities of such large grains steadily for months on end would require some robust mechanism. Comets don't typically spray out almost sand-sized particles in such a consistent way. All of this leads toward the 12th entry, the one that has drawn the most attention lately. It has to do with rotation, or rather, the lack of its fingerprints in the jets. Back in July and August, observers measured 3I-ATLAS rotating every 16.16 hours. There is no known process that would suddenly stop such a spin in the emptiness of space. If the nucleus is still rotating, then anything fixed on its surface, like a vent spraying gas, should produce structures that show that rotation at the expected outflow speed of around 400 meters per second. It takes about a month for material to travel 1 million kilometers. Over that month, with a 16-hour spin, the comet should whirl around roughly 45 times. Each rotation should bend or segment the jet a little, leaving subtle wiggles or gaps like the marks left by a spinning garden sprinkler as it throws water into the air. But the long, narrow jets seen in November, both in professional images and in the amateur's stacked photograph, show no such signatures. They are straight and smooth, as if their source were not rotating at all, or as if whatever is tracing them is not tied to the spinning nucleus in the usual way. Loeb offers 3 broad possibilities for this, each one sitting uncomfortably beside the others. In the first, the jets are really the evaporating trails of fragments that were thrown off in a single, violent event near perihelion. Large chunks, launched all at once, would move in straight lines, and the gas and dust that boil off them as they heat up would trace those same straight paths. That would give you long, narrow features that don't smear with the nucleus's rotation. But this picture pushes against the fact that the nucleus appears intact. An explosion big enough to launch many massive fragments should have left scars. In the second scenario, the jets come from active vents on the nucleus that switch on and off depending on how they face the sunday. If a particular vent only blows when it is illuminated, and if the rotation and orbital motion line up just so, The same region could face the sun at nearly the same point in space over and over, creating a jet that looks straight when we integrate its light over time. It's a delicate bit of timing and geometry, not impossible, but a stretch. The third possibility is the one that makes many of his colleagues uneasy, that these are not natural vents at all, but thrusters. In that view, the jets preserve a global orientation because they are being steered, used for navigation. Loeb doesn't claim this is true. He lists it because, logically, it is one of the options the data allow, and to erase it from the page without looking would feel to him like turning away from a question because it is uncomfortable. That willingness to leave the technological hypothesis on the table, even as a distant third choice, is what frustrates many other astronomers. They are wary of feeding internet fantasies and prefer to say, simply and firmly, that 3IATLAS is a comet and leave it there for now. Loeb, instead, stays close to the measurements themselves. For him, the strangeness of those numbers means no possibility should be dismissed too soon. The X-shaped pattern revealed on November 20th adds another layer to this unease. If those sideways jets are real structures in space and not just a satellite streak or some other observational glitch, they don't fit comfortably into any of our standard comet mechanisms. They are perpendicular to the Sun-comet line, extend for about 1 million kilometers, show no hint of rotational smearing, and, if his interpretation is right, may trace the paths of many separate objects that left the vicinity of 3IATLAS around perihelion. If that is what we are seeing, then we are watching something truly new, either a natural fragmentation event that somehow launched numerous pieces along remarkably straight, collimated paths, or a deliberate release of smaller components from a larger body. And then the simplest, softest question rises and does not quite go away. If 3IATLAS really did release many objects, where are they now? At 500 meters per second, 22 days of travel brings them about 1 million kilometers from their starting point. By December 19th, after 51 days, they would be roughly 2.2 million kilometers from the main body, still close enough in cosmic terms to be related, but far enough that, with the right instruments and the right attention, they might be seen as separate, tiny travelers in the dark. Whether those small companions would turn out to be nothing more than oddly behaving ice fragments, or something more deliberate, is the quiet puzzle waiting there in the space between them. If Loeb is right about those sideways lines, if they really are trails and not a passing satellite scratch across the image, then the little question that follows is surprisingly tender. What, exactly, has been leaving them behind? The first place the mind goes is the simplest one. Picture 3IATLAS as a loose bundle of ice and rock that has wandered the galaxy for an almost unimaginable time. Out in interstellar space, it would have been battered by cosmic rays, tapped by dust grains at high speed, nudged by faint encounters with other stars. That kind of long exposure slowly fills an object with hairline fractures and hidden weaknesses. For ages, nothing much happens. Then, at last, it swings close to a star, and everything changes. Near perihelion, the surface temperature can jump by hundreds of degrees. Ice that has slept for eons begins to boil straight into gas. Gases trapped in pockets under a tougher crust push outward with growing pressure. The shell creaks, swells, and sometimes fails. We've seen comets crack and break under that kind of stress before, some splitting into chains of pieces, some disintegrating entirely as they rush toward the sunday. Fragmentation, in that sense, is not unusual. It's almost part of a comet's life story. So, if smaller objects really did peel away from 3IATLAS near perihelion, the default sleepy assumption is that they are natural fragments, chunks of ice and rock liberated by heat and pressure. That would be the calmest answer, and in many ways the most comforting. But this is where the details begin to tug at the sleeve. A natural fragment doesn't glide like a polished bullet. Once it leaves the parent body, it starts its own messy life as a tiny comet. It tumbles, its surface heats unevenly. Fresh jets of gas burst from new cracks, pushing it in small, unpredictable ways. Its path becomes a little chaotic. If many fragments break off, they spread into a fuzzy cloud, a widening smear of debris. Over time, the structure softens, edges blur. What the November 20th image seems to show, if it holds up, isn't a cloud. It looks more like two very straight strokes drawn across space, both at right angles to the usual sun-comet line. That kind of tidy collimation, that almost geometric precision, it is hard to get from a spray of crumbling ice, unless the more cautious voices say, we aren't really seeing the fragments themselves at all. One way to picture it is to think about the sky behind an airplane. The plane may weave and tilt, but from far away, its contrail can look like a clean, simple line. In the same way, if fragments shot away from 3IATLAS in two narrow cones, one above the orbital plane and one below, and then shed dust as they went, the dust could trace out straight-looking stripes. When we stack many images together, the fragments might themselves be tumbling and evolving, while their combined trails give our eyes the impression of stable rails. That idea would make many astronomers exhale in relief. It sounds like something nature could manage. Still, it leaves an odd piece on the table. When comets break, the fragments usually fly out in many directions at once, like pieces from a bursting bubble. You get a roughly expanding shell, not two disciplined jets. To get that kind of directionality, the nucleus would need a particular weakness, perhaps a long crack that failed in a preferred orientation. For that crack to happen to point perpendicular to the Sun-comet axis would be a coincidence, not impossible, but another small roll of the cosmic dice. Loeb has played with the numbers for the natural fragments picture. If the mini-objects began their journey around perihelion on October 29th and have traveled about 1 million kilometers by the time of the November 20th image, then their average drift relative to 3IATLAS is about 500 meters per second. That's quicker than the gentle to 400 meter per second flows we often associate with outgassing, but not by a wild amount. A sudden, explosive release of trapped gas could plausibly hurl chunks that fast. We've seen comets undergo outbursts where material is thrown off with surprising vigor. So the speed alone doesn't demand anything artificial. It fits inside the edges of what natural outbursts can do. What tugs at him is not just the speed, but the way those trails hold their form. If these are merely loose piles of ice and dust, drifting away from the main body, they should be changing. As they move farther from the sun, individual pieces should crack further, sublimate, and shed their own fuzzy tails. Within weeks, the clear, narrow lines should blur into the general haze of the coma, becoming part of the background. If, after 22 days, the features are still long, straight, and sharply defined, then whatever is tracing them has to be more robust than a casual snowball. It needs structural strength. It needs to behave like something that can hold itself together over time. That's the point where the other possibility, the one many people would rather not say out loud, steps quietly into the room. In that picture, the mini objects aren't fragments at all, but probes, small craft released by a larger one to fan out and take a closer look at different places. The idea isn't pulled from science fiction as much as it is borrowed from our own habits. When we send a big mission into the outer solar system, we often tuck smaller vehicles inside. Cassini carried Huygens to Titan. The Galileo orbiter dropped a probe into Jupiter's atmosphere. It's a simple, practical architecture. Let the main craft carry the fuel and communications, and let smaller pieces do the risky, targeted work. Now imagine something similar on an interstellar scale. A craft like 3IATLAS crosses our system at tens of kilometers per second. Slowing down to park in orbit around a planet would demand enormous energy, far more than a modest probe might have. So instead of braking, it glides through, and as it nears the inner planets, it releases smaller units that can tweak their paths just enough to skim past Mars, or Earth, or Venus, or Jupiter's high cloud tops. Each one might have its own thrusters, its own instruments, its own tiny transmitter linking back to the parent. If that is the architecture, then those straight, unsmeared trails suddenly make a different kind of sense. The mini-objects wouldn't care about the parent's rotation. They would maintain their own orientation and adjust their own thrust, drawing long, stable lines across space as they go. From a distance, we wouldn't see the probes themselves, only the faint, persistent exhaust they leave behind. It's an idea that can make the heartbeat a little harder, but Loeb presents it carefully, not as a conclusion, just as a scenario that fits the known pieces without bending them too far. The essential question becomes, how could we tell the difference? One of the clearest tests would be written in the speed of the jets. There's a natural ceiling to how fast sublimating gas can flow from a sun-warmed surface. For ordinary cometary materials, at a few hundred degrees, that top speed hovers around 400 meters per second, roughly the sound speed in such a gas. Chemical rockets, by contrast, spit exhaust several kilometers per second, often between 3 and 5. Ion thrusters accelerate particles even faster, 10, 20, 50 kilometers per second. Measure the motion of material in those strange lines, and you get a strong hint. Are we looking at breath or at machinery? Another test is in the recipe of the gas and dust themselves. Natural comet jets are mostly water vapor, with helpings of carbon monoxide, carbon dioxide, and traces of other simple molecules. If spectroscopic observations of those sideways features were to reveal unusual elements or compounds, something that looks more like a fuel mix than a frozen lake bed, that would be a heavy clue. Even a normal composition, though, would still be valuable. If the jets are flowing at natural speeds with natural ingredients, the scale tips back toward exotic but unintentional physics. A third way would be to look directly for the many objects, not just their trails. If there really are compact bodies a couple of million kilometers from 3IATLAS, they might show up as small points of light in high-resolution images, or as subtle bumps in the brightness distribution of the coma. With the right instruments, and with enough patience, they might become visible as separate dots, like faint fireflies clustered near a brighter lantern. This is why December 19th holds such quiet importance. At its closest to Earth, 3IATLAS will still be far, about 269 million kilometers, but that's near enough for Hubble to resolve structures a few hundred kilometers across, and near enough for Webb to gather detailed spectra of its gas and dust. Large telescopes on the ground, using adaptive optics to sharpen their view, might also pick out small companions if they're there and bright enough. Loeb has been calling, gently but persistently, for a coordinated effort. Space telescopes, ground-based observatories, as many eyes as possible turned toward this one traveler during that short window. The technical side of this is not the obstacle. We point our best instruments at comets all the time. What hesitates is something more human. Many astronomers are wary of giving the artificial hypothesis too much air. They worry that dedicating Hubble or Webb time to test such a possibility will be seen as indulging fringe ideas, encouraging those parts of the internet that shout alien mothership at the slightest oddity. They worry about opening the door to a flood of similar requests. Every lumpy asteroid, every dusty comet, suddenly framed as potential hardware. Loeb's answer is simple in spirit, even if it's uncomfortable in practice. Science, he says, doesn't protect its dignity by refusing to look at strange things. It protects its dignity by looking carefully and honestly, and then telling the truth about what it finds. If 3IATLAS turns out to be entirely natural, the most anomalous natural comet we've ever studied, then close observations will refine our understanding of interstellar bodies and the range of comet physics. If, against the odds, it turns out to be something else, if even one piece of evidence stubbornly refuses a natural explanation, then the implications are so deep that not looking would feel like turning our back on the cosmos itself. There is also the quiet, almost melancholy thought that if 3IATLAS is a probe, it was launched a very long time ago. At its current speed and angle, Loeb estimates it may have been traveling for hundreds of millions, even billions of years. Civilizations rise and fall in time spans shorter than that. Stars swell and fade. Planets freeze and burn. It could be that whoever sent this object on its way is long gone, their worlds reduced to ash and dust, leaving only this mute visitor as a record that they once wondered and reached outward. Or perhaps not. Perhaps somewhere, around some distant sun, the descendants of its builders or their silent machines still wait for signals, still collect the trickle of data from craft launched before humanity ever walked the earth. The thought is both awe-inspiring and unsettling, to imagine that our little blue world is now briefly crossing the sight line of a project older than our entire species. While scientists weigh these possibilities with care, the noisier corners of the internet have already made up their minds. Some see the X pattern and declare it a sign of steering. They see the anti-tail and call it maneuvering. They hear NASA's cautious language and read it as proof of a cover-up in their story. The conclusion came first, and the data are just decorations. NASA, for its part, seems to be walking a very narrow ridge. They have the same images everyone else does. They have the Mars orbit data, where the X can be seen. They released that image to the world, and yet they did not linger on that feature in their November briefing. They presented it as one frame among many, part of a broader, calmer narrative about an interstellar comet behaving in mostly comet-like ways. They did not stand up and say, "Look, there's a geometric structure we don't understand." You can feel the reasoning behind that restraint. They do not want to set the speculation engine spinning faster than it already is. They prefer to let the community move slowly through papers and peer review rather than through headlines and viral clips. That is, in many ways, the responsible path, but it leaves empty space where public curiosity naturally flows. And in that empty space, stories grow. Stories about what might be hidden, about what someone, somewhere, perhaps knows and isn't saying. So here we are, in that quiet, uneasy middle. There is an interstellar object passing through our neighborhood, with 12 carefully logged anomalies in its behavior. There is evidence still tentative, still debated, of a geometric pattern in the material that flows around it. A pattern that could be the work of some highly organized natural process we don't yet grasp. or the shadow of deliberate structure written in dust and light? For now, all of that rests on something very simple: time. There is only a short stretch left before 3IATLAS makes its closest pass by Earth, and within that month sits a narrow window where the right kind of observations could soften this story one way or the other. In the quiet between images and press releases, the question stays the same, almost childlike in its simplicity. Is this just a very odd comet, or is it something we ought to treat with a different kind of attention? Wrapped around that question is another thread, less about physics and more about people, about what happens when the usual flow of information is suddenly pinched shut. In the United States, the government shutdown began on October 1st. For anyone far from that world, a shutdown is what happens when Congress fails to agree on a budget. Federal agencies lose their fresh authorization to spend, and many employees are told to stop work. Offices empty, non-essential tasks pause. For a place like NASA, that doesn't mean spacecraft fall silent. They keep following their pre-planned instructions, but it does mean that public communication slows to a thin drip or stops altogether. For 3IATLAS, the timing could hardly have been worse. October 1st fell, just 3 days before the object swept closest to Mars, 4 weeks before perihelion. Right as it was entering the most revealing phase of its passage, it was the moment when every lens and sensor pointed its way would be most valuable, not just for gathering raw data, but for feeding that data quickly into the hands and minds that could decide what to do next. The machines kept going. The Deep Space Network listened. Orbiters around Mars, including the Mars Reconnaissance Orbiter, carried out their imaging sequences on October 2nd and 3rd. MAVEN continued to sniff the thin gases around the red planet, and for a brief time, the halo of hydrogen around the comet itself. The flow of bits from space to Earth did not stop. What did stop, or at least slow to a near hush, was the human part. The people who process those bits into calibrated images, who write up the initial findings, who schedule and announce follow-up observations, were sent home, legally forbidden to work. Daily updates vanished. Trajectory refinements, spectral interpretations, simple, "Here is what we're seeing," notes, everything that usually builds a shared understanding in real time went dark, into that silence, as it always does. Imagination poured in to fill the gaps. NASA has built a reputation over decades as being remarkably open. When such an organization suddenly quiets down at the most interesting moment of a strange object's journey, many minds don't default to paperwork as the explanation. They reach for the more dramatic thought. Something is being hidden, something too unsettling or too uncertain to share. Avi Loeb felt that silence like a physical weight. In blog posts and interviews, he didn't hide his anger. On a long conversation with Joe Rogan in early November, with the shutdown just ended and little new data yet released, he said plainly that the timing felt like a worst-case scenario. Right when 3IATLAS was skimming near Mars, racing toward perihelion, perhaps shedding material or changing in ways we could only catch once, the channels he relied on to see that story unfold went blank. For someone who already believes the scientific establishment is too cautious with anomalies, too quick to file them under probably nothing, the shutdown felt less like an accident and more like confirmation of that worry, even if, officially, it had nothing to do with astronomy at all. The formal explanation is prosaic. NASA staff were furloughed because of a budget impasse. They could not log in, run pipelines, draft releases, answer journalists. Spacecraft, already programmed, simply did what they were told to do weeks or months earlier. The data came in and piled up in queues, waiting for the people who would eventually wake those numbers into meaning. That story may be entirely true. There's no need for a secret motive to explain it. But even if the cause is purely bureaucratic, the effect is still worth tracing. Because in that 41-day stretch, the sky kept moving. While offices were dark, 3IATLAS was not waiting. We do know a little about what was captured in that time. On October 2nd, the Mars Reconnaissance Orbiter turned its HiRISE camera toward the interstellar visitor from about 19 million miles away, roughly 30 million kilometers. HiRISE is an extraordinarily sharp eye. On Mars, it can see details the size of a paving stone, used on a comet. At such a distance, it can't give that kind of intimacy, but it can still resolve structures tens of kilometers across, enough to distinguish the nucleus from its surrounding glow, enough to see broad jet geometry. What it recorded, when people finally had time to process the frames, included the now famous X pattern, 4 directions of material streaming out where textbooks would have suggested 1 or 2. That image was not shown to the world until November 19th, 48 days later. And when it was finally released, it appeared as one figure among many, a single panel in a larger collage, noted but not dwelt upon. On paper, the delay traces straight back to the shutdown. The spacecraft beamed its pictures down through the Deep Space Network on schedule, but the folks who transform raw data into public products were unavailable. The images joined the queue, waiting for October's politics to thaw. All the while, online conversations about 3IATLAS were growing louder and wilder. Loeb argues that those lost weeks were not just a public relations problem, they were scientifically expensive. If the HiRISE image had been processed and shared in early October, if the clear X had been known then, rather than in mid-November, there might have been time to organize a more aggressive response, to retarget other spacecraft, to ask for rapid turnaround observations from Hubble or Webb, while the object was still relatively close to Mars, still near its peak activity. By November 19th, that optimal window had narrowed. Perihelion was already behind it. 3IATLAS was on the outward leg of its swing, a little farther, a little dimmer each day. There were still opportunities, still things to learn, but some of the sharpest chances had quietly passed while the lights were off. Maven, too, had its brief moment with the visitor. On October 9th, its instruments picked up the huge hydrogen cloud surrounding 3IATLAS, evidence of water molecules being broken apart by sunlight and sending their lightest component drifting outward. The halo it saw was enormous, about 200,000 kilometers across, larger than the distance from Earth to the Moon. That image, and the estimate of the coma's size, also waited until November 19th to be shown. What Maven may have seen in other channels' ions, unusual plasma behavior, subtle fingerprints of the outflow, remains a quieter question. Its sensors are tuned to feel the tug and texture of the solar wind on Mars's atmosphere. If anything about 3IATLAS's interaction with that wind was out of the ordinary, Maven is one of the craft that could have noticed. Whether those data show nothing unusual or something still being parsed, we simply don't yet know. If we do, the story hasn't yet been told clearly in public. Across the Atlantic, the European Space Agency was untouched by the US shutdown. Their orbiters, Mars Express and the ExoMars Trace Gas Orbiter, continued their routines. On October 3rd, TGO caught 3IATLAS as a slightly fuzzy point moving against the starfield, about 32 million kilometers away. The images, modest in detail but clean, were released just a few days later, on October 7th. More importantly, ESA used those observations not just as pictures, but as measurements. By comparing the comet's actual position in the sky to the predicted one, they teased out small differences, tiny offsets that signaled non-gravitational acceleration. In other words, the jets of gas and dust were indeed pushing the object off the path it would have followed under gravity alone. The effect was small, only a few thousand kilometers, deviation over vast distances, but real. On October 22nd, ESA wrote up and shared that analysis, folding the new numbers into better future predictions of where 3IATLAS would wander. For active comets, this is standard practice. You watch, you see the little pushes, you refine. What was unusual was that, during this time, NASA had nothing to say in public, no confirmation, no complementary analysis, no sense of how their own spacecraft were seeing the same events. It was not that their machines were blind, it was that their voice was absent. That silence became fertile soil. On message boards and social media, people speculated freely. Threads blossomed with claims that the object had changed course toward Earth, that secret radio signals had been detected, that trajectories were being updated but hidden. None of it was grounded in released data. It was grounded in anxiety and imagination. Without regular, sober updates from the usual trusted channels, those stories spread as if they were plausible. When Loeb sat down in front of microphones on November 7th, the shutdown had technically ended, but its after effects still lingered. For over an hour, he talked about 3IATLAS, about the anomalies, about the possibility stated carefully but firmly that it might be something more than a natural snowball, about his frustration with the pace and tone of official communication. He also shared something that stuck with many listeners, that an academic journal had pushed back on one line in his paper, a line suggesting that the object's path might have been designed. The editors, he said, felt that line stepped from cautious hypothesis into sensational territory. They wanted it gone. He chose to leave it in and instead posted the full paper to a preprint archive, where anyone can read it, but where it still waits outside the formal stamp of peer review. For him, this was not just a small editorial disagreement. It was another example in a pattern, a system reluctant to even entertain certain possibilities, even when the data do not sit comfortably in the usual boxes. Many astronomers disagree with his interpretation of the object, but even those who think all 12 anomalies can eventually be folded back into natural explanations tend to acknowledge one thing: the shutdown cost time. Time while 3IATLAS was brightest, most active, closest to some of our best instruments. Time when decisions to point or repoint could have made the difference between seeing something clearly and missing it entirely. Now, as the object heads outward, each night puts a little more distance between us and its most revealing days near the Sunday. By December 19th, when it brushes past at its closest to Earth, it will still be within reach of our best telescopes, but the roaring phase of its activity will be behind it. Jets will be weaker, the coma will shrink. We will still learn a great deal, but we will be, in a sense, reading the echoes rather than hearing the first loud notes. Was any of this deliberate? Almost certainly not. The budget standoff that triggered the shutdown was about domestic spending, political positioning, and long-running disagreements that have nothing to do with interstellar comets. The fact that 3IATLAS reached perihelion and swept near Mars in the middle of that argument looks, from every reasonable angle, like an unfortunate coincidence. But coincidences can feel like designs when information is scarce. The longer NASA remained quiet, the more the timing looked, to some, like intent. In that gap, questions multiplied. What did Maven's particle instruments see as 3IATLAS passed near Mars? Did any of the rovers on the surface, Curiosity or Perseverance, tilt their cameras up and try to catch the visitor as a tiny moving point above the dusty horizon? If they did, where are those pictures in the public archives? What did solar watching missions like SOHO record as the comet threaded through their fields of view between mid-October and late October? Those missions routinely capture comets swooping close to our star in white light and coronagraph images. Somewhere, there may be time-lapse sequences of 3IATLAS, as no one has yet seen it. Some of that material has trickled out already. Some of it is still moving through pipelines, being calibrated and checked. Some of it may never be shown widely, not because of a grand decision, but simply because there is only so much human time to go around. 15 spacecraft watching one object can easily generate more data than a small group of teams can comfortably digest in a few months. From the inside, that looks like being overwhelmed. From the outside, looking up into a sky that feels suddenly more mysterious than usual, it can look like something else. And perception has its own gravity. A gap in communication doesn't just leave questions about a comet. It can slowly erode trust in the institutions that watch the sky for all of us, making future silences feel heavier and future reassurances shorter than they were meant to be. Among all the strange things about 3IATLAS, there is one feature that seems to bother physicists the most. It's that thin, stubborn line of light pointing the wrong way, the anti-tail that refuses to behave like an illusion. In ordinary comets, an anti-tail is a trick of geometry. As a comet warms, its ices turn straight from solid to gas, carrying dust away. The finest grains, barely larger than smoke particles, feel the push of sunlight and the solar wind and stream outward, forming the classic tail that points away from the sunday. Slightly larger grains, heavier and more stubborn, tend to lag along the comet's path instead, tracing out a curved ribbon that marks where it has been. From Earth, we never see this in a simple, flat way. We're always looking from some particular angle, with the comet's orbit tilted this way or that. Sometimes, that curve of heavy dust lines up with our line of sight just right, and it looks as though a tail is pointing toward the sun instead of away. That is the traditional anti-tail, a perspective trick. Once you draw the orbit in 3 dimensions and put the observer in the right place, the illusion dissolves. The dust was never truly flowing sunward at all. With 3IATLAS, that comforting explanation doesn't seem to work. Loeb and others have sat with the geometry, tilted the orbit, shifted the viewpoint, done all the quiet trigonometry that usually makes the paradox vanish. And the result, to their discomfort, is that this time, the feature appears to be what it seems, a real stream of material heading almost directly toward the sun, not just along the orbit, not merely skewed by perspective. To make that possible, you have to think in terms of momentum. Loeb's team estimates that, if this interpretation is right, the particles in that sunward stream would need to be large by comet standards, about 100 micrometers in radius, something like a fine grain of sand. That doesn't sound large, but compared to the usual dust in a comet's coma, it's huge, roughly 1,000,000 times more massive than the tiny soot-like grains that make most tails glow. The solar wind, a thin stream of fast-moving charged particles, can push the very smallest grains around with ease. But at Earth's distance from the sun, that wind is still an exquisite vacuum by earthly standards. When it hits a grain of sand, the grain mostly shrugs and keeps moving in the direction it already has. If 3IATLAS is throwing such grains sunward with enough speed, They will initially punch through the flow of particles, carving a narrow, bright lane back toward the light. Eventually, the push of the solar wind builds up enough to balance their forward motion. They slow, stall, and are turned aside. The distance at which that balance is reached, in Loeb's calculations, is around 1,000,000 kilometers from the nucleus. In the November 9th image taken by Frank Nebling and Michael Buchner, the anti-tail seems to fade at roughly that scale. At first glance, the numbers and the picture fit neatly, almost too neatly, but that just shifts the puzzle to a deeper level. To throw sand-sized particles sunward at hundreds of meters per second is not something a gentle, simmering comet does easily. Typical outgassing speeds for natural sublimation hover in the low hundreds of meters per second, and that's for lifting light dust. Heavy grains cling harder to the surface. You need pressure to rip them free confined gas beneath a crust, suddenly released. You need little explosions. Comets do have outbursts like that, localized eruptions, when a sealed pocket of gas finds a weakness, and vents, flinging material into space. We've watched such events on other comets, brightening them overnight and spraying debris, but they tend to be brief and patchy, like occasional coughs, not a steady exhale. 3IATLAS, if the anti-tail is what it appears to be, has been producing a sunward stream since July, about 5 months of continuous or near-continuous activity in one preferred direction. The energy budget implied by that is unsettling. Loeb's rough estimate is that to sustain the observed anti-tail, 3IATLAS would have to be losing on the order of 50 billion tons of material each month. That works out to about 1% of its estimated mass being shed every 30 days. Kept up for long, that kind of mass loss would hollow a comet out in just a few years. Normal comets can erode fast, but not usually like this, and not with such apparent discipline. So either the rate is being overestimated, meaning some other mechanism is painting that sunward streak, or the rate is roughly right, and we are watching an object slowly consume itself in a highly organized way. There is another, softer possibility that pulls the mind away from dust and towards something more invisible. What if the anti-tail is not built from grains at all, but from gas, specifically ionized gas, plasma, material whose atoms have been stripped of some electrons and now respond less to wind pressure and more to magnetic fields? The sun's magnetic field is not a simple bar magnet. It is twisted and tangled, its lines looping outward and back, woven into the solar wind. If 3IATLAS were somehow releasing ionized material, that charged gas could be guided along those invisible rails. From our vantage point, some of those field lines might bend back toward the sun, giving the appearance of a sunward jet, even though the true driving force would be magnetic structure rather than sheer momentum against the wind. The difficulty is that most comets do not start off strongly ionized. Their gases leave the nucleus as neutral molecules and become ionized further out under the influence of solar ultraviolet light and the ambient plasma. They tend to be passive passengers in the magnetic environment, not active sculptors. For 3IATLAS to be different, something about its composition or its surface processes would have to be unusual, perhaps releasing pre-ionized material or generating electric currents that shape its surroundings more strongly than a typical icy body. That is where the speculation begins to feel delicate. If an object in space sustains strong, organized electrical effects, or keeps ejecting large, fast particles in a persistent pattern, one way to make sense of it is to imagine an internal energy source, something deeper and more stable than sunlight falling on a rough surface. Radioactive decay can provide a little heat over long times, but not the kind of vigorous, directed activity we seem to be seeing. Tidal heating can warm moons that circle giant planets, but 3IATLAS is not bound closely enough to any world for that to help. So where, if the observations are right, does the extra energy come from? There are still natural cards to play. Perhaps 3IATLAS formed with an unusually rich mix of highly volatile ices, materials that remain frozen in deep interstellar cold, but erupt energetically when warmed even a little. Perhaps its interior is layered, with different kinds of ices stratified at different depths. As the outer layers boil away, fresh ones are exposed, each with their own temperature thresholds, creating a staggered series of outgassing stages that mimic a sustained power source. Perhaps its rotation, shape, and internal structure combine just so, with pockets and fractures positioned in a way that channels gas into preferred jets for months at a time. Given enough time and enough variety in the universe, even very specific arrangements can occur naturally. But the more specific the requirements become, the more the mind quietly notices how organized the system must be. Not organized in the sense of polished metal and straight edges, but in the sense of a structure that seems tuned, multiple layers, multiple stages, directions that hold steady over long months. The line between extreme example of nature's variety and something that feels arranged can grow thin in that place, especially when the object already carries 11 other small oddities in its wake. An image from November 15th, taken by Tirasak Talawang from a telescope in Thailand, added yet another layer of complexity. It showed not just a single anti-tail, but a whole fan of structure. A prominent sunward streak, and at least two more conventional tails, pointing generally away from the sun, diverging at angles like the prongs of a fork. Such multiple tails are not unheard of. Comet Hale-Bopp, for example, displayed both a dust tail and a gas tail, each shaped differently by light and the solar wind, but in that case, all of them leaned away from the sun, obedient to radiation and wind. For 3IATLAS, one of the main features points back toward the light instead, as though some part of the comet has chosen to row upstream. That is the heart of the discomfort. Multiple tails alone are not alarming. It is the direction of one of them, and the way it persists, that keeps drawing eyes back. When you follow that line of thought out to the edge, the choice it presents is not especially comfortable. Either 3IATLAS is showing us a combination of natural behaviors that can, in principle, arise, but almost never do a comet at the far edge of what ice and dust and sunlight can manage, or it is doing something that lies outside the toolkit we have built from past comets, something that might require us to think in terms of internal engines rather than passive evaporation. There isn't much room for a gentle middle, a mostly ordinary, with a tiny twist. The twist here is the story, and somewhere in that narrow sunward line, drawn like a faint stroke toward the star, the universe is quietly inviting us to decide how seriously we are willing to take what we see. By now, it almost feels as if 3IATLAS is standing at the edge of what we're willing to call normal, holding out these thin, bright threads and asking how many exceptions we can stack before the word loses its meaning. A single odd feature is easy to live with. Two or three can be folded into nature has a long tail of possibilities. But when each new observation adds another detail that doesn't quite sit inside the model, the quiet question becomes harder to ignore. Are we misunderstanding the object, or are we asking it to live inside the wrong model altogether? The antitail is only one tile in that mosaic, but it's a stubborn one. It keeps refusing to click into place without bending something else. Those 50 billion tons per month live in the same uneasy space. The number sounds outrageous when you first hear it, like a comet ripping itself apart in slow motion. But numbers can be dramatic without being very informative unless you hold them up against something. The first thing to ask is simple. 50 billion tons out of how much? We don't know the nucleus size precisely. Hubble's view, blurred by the surrounding coma, suggests a diameter somewhere between a few hundred meters and several kilometers. At the small end, around 440 meters across, a typical comet density would give a total mass on the order of 20 billion tons. At the large end, 5 or 6 kilometers, the mass climbs into tens of trillions of tons. It's like trying to guess the size of a stone hidden inside a lantern just by how bright the lantern looks. Loeb approached the question from a different angle. If a comet is venting gas strongly, its jets act like tiny thrusters, and its orbit should deviate slightly from the track gravity alone would dictate. Before October, 3IATLAS showed very little of that non-gravitational wobble. From that lack of detectable push, he estimated a minimum mass, the smallest the nucleus could be, and still shrug off the outgassing we know was happening. That floor comes out around 33 billion tons. The real mass could be more, it just can't be comfortably less. Set that beside 50 billion tons per month, and the tension is obvious. If those two numbers both apply over long stretches, the comet would be hollowed out in less time than a calendar page. That tells us that at least one of the assumptions, the minimum mass, the mass loss rate, or the idea that the loss is steady, isn't painting the whole picture. The mass loss estimate itself comes from looking not at the nucleus, but at the faint material stretching away from it. Even when a jet is unimaginably thin, only a handful of particles in each cubic centimeter, if it runs for 1,000,000 kilometers and spreads hundreds of thousands of kilometers across, the total volume is enormous. Multiply a tiny density by a gigantic space, and you can still end up with a lot of stuff. To turn those wisps into a total, you have to assume how fast the material is moving. If it's drifting outward at roughly 400 meters per second, the kind of speed we expect from gas boiled off by sunlight, you need a certain flow of mass per second to keep the jet filled to the brightness we see. Integrate that flow over a month, and you get the famous 50 billion tons. But if that speed is higher, the picture changes. Faster outflow means the same amount of light can be produced with less mass. The particles spend less time in the illuminated region, so fewer of them are present at once. Double the velocity, and the required mass loss rate roughly halves. At 2 kilometers per second instead of 400 meters per second, the monthly loss might be closer to 10 billion tons. A heavy cost, but not an impossible one. That's why the velocity of these jets is such a crucial number. It doesn't just tell you how hard the comet is breathing. It hints at how it's breathing. Natural sublimation has trouble pushing gas much faster than a few hundred meters per second at the temperatures involved. Chemical rockets happily throw exhaust out at 3 to 5 kilometers per second. Ion drives go faster still. Right now, we're in an awkward in-between. To know the true speed, you would need high-resolution spectroscopy, careful measurements of tiny shifts and spectral lines along the jet, taken with instruments like those on Hubble or Webb. Those would show whether the gas is drifting along at hundreds of meters per second or racing at a few kilometers per second. Until then, we're left with theory-guided guesses, and the difference between those two regimes is the difference between a frantic, self-destructive snowball and something that looks suspiciously like an engine plume. Even if we stay strictly inside the natural camp for a moment and accept the 400 meter per second assumption, the 50 billion ton figure doesn't automatically mean doom. Comets are not steady fountains. Their activity swells and sinks. They brighten as they fall inward, flare near perihelion, and then quieten as they move away. If 3IATLAS was losing only 1 billion tons per month on the way in, then surged to 50 billion around perihelion for a few weeks, and then calmed down again as it recedes, the average over its whole passage through the inner system could be much lower, perhaps 10 or 20 billion tons in total. A large enough nucleus could survive that, bruised but intact. The pattern of that activity, though, is what keeps catching attention. Instead of a smooth, predictable ramp-up, 3IATLAS seems to have changed gears in steps. Before perihelion, it looked oddly quiet for something that would later show such dramatic jets. After perihelion, new structures appeared, pointing in directions that hadn't been visible before, as if the object had suddenly found new ways to vent. One natural picture for that sort of behavior is fragmentation, not a dramatic shattering into a spray of separate comets, but a more subtle cracking. If the nucleus developed large internal fractures near perihelion, a few big pieces could begin to drift slightly apart while still sharing a common envelope of gas and dust. Each piece would then act like a smaller comet, developing its own jets. The overall brightness and complexity of the outflow would jump, not because anything supernatural had happened, but because you now have several sources instead of one. The trouble is that, so far, our images don't clearly show a swarm. High-quality observations from November still present 3IATLAS as a single, bright, central condensation. If fragments exist, they must either be too small and faint for us to separate from the glare, or still so close together that they blend into one unresolved blur. As time passes and the gas thins, any significant chunks should drift far enough apart for sharp-eyed telescopes to start teasing them apart. If we reach that December window and still see only a single, solid-looking nucleus, the hidden cluster explanation will start to feel thin. Fold all of this back into the energy budget, and the balance becomes delicate. At perihelion, an object the size of a few kilometers sitting where 3IATLAS sat would intercept on the order of a few tens of gigawatts of sunlight. That's a lot on human scales comparable to dozens of big power plants, but on cosmic scales, it's just a trickle. Not all of that energy goes into throwing material off the surface. Much of it is reflected or re-radiated away as heat. Only a fraction can be converted into the kinetic energy of gas and dust. Run the numbers carefully, and you find that a few gigawatts of useful power could just barely be enough to loft 50 billion tons of material a month to a few hundred meters per second. There isn't much room above that. If the mass loss is higher than we think, or the gas is moving faster, the sunlight alone starts to fall short. In that case, you either adjust the mass loss downward, increase the effective absorbing area, or go looking for extra energy in places we don't usually have to look for comets. One such natural reservoir lives in the composition itself. Out in the deep cold of interstellar space, ice is more volatile than water. Nitrogen, methane, other fragile molecules can remain frozen for billions of years. We see such ices on distant worlds, in our own system, on Pluto, on Triton, on other far-flung surfaces that never warm above tens of degrees above absolute zero. If 3IATLAS formed in a place rich in those supervolatiles and then buried them under thicker layers of water and carbon dioxide ice, it could have carried a kind of internal battery all this time. As it approaches a star, the surface warms first. Ordinary ices begin to sublimate, slowly thinning the outer shell. Deeper inside, more volatile layers remain locked and pressurized. When the warming front reaches them, perhaps near perihelion, they can erupt explosively, releasing gas with far more energy than sunlight alone would suggest, dragging huge amounts of material with them. The result could be a temporary, violent increase in activity that looks from the outside like an engine suddenly opening its throttle. That scenario is entirely natural. It doesn't require technology, only the right ingredients stacked in the right order and a long, patient wait. But you can feel, even in that explanation, how specific the conditions have to be. A particular formation environment, a layered interior that stayed intact for eons, cracks that open at just the right time during this one brief swing around a star. And that, in a way, is the pattern that keeps returning. Every anomaly can be met with a natural maybe. Maybe the dust is unusually big. Maybe the jet's unusually fast. Maybe the interior unusually stratified. Maybe fragmentation happened just so. Each answer is possible. None of them, on its own, breaks physics, but each one asks 3IATLAS to be special in a slightly different way. After a while, you find yourself looking at an object that must be extraordinary in a dozen separate dimensions at once: composition, structure, timing, activity, geometry, or else you admit that your idea of what ordinary interstellar comets look like might be incomplete. Perhaps the galaxy is richer in wild, hyperactive wanderers than our brief sample suggests. Perhaps we have simply been lucky or unobservant until now. Or perhaps 3IATLAS really is an outlier, a single peculiar visitor whose path and behavior carry a story that will not repeat for a very long time. In either case, it feels less and less like something to glance at and then file away as just a comet, and more like something that deserves, at the very least, our full, awake attention before it slips back into the dark and takes its answers with it. If 3IATLAS really is more than ice and rock, if it is some kind of probe or carrier or long sleeping machine, then there is a simple, almost childlike expectation that follows. Somewhere, somehow, it should be saying something. Every spacecraft we've ever built does. Even the quietest of them talk in small, patient whispers, narrow streams of radio waves, carrying bits of temperature, magnetic field readings, images of distant moons. Voyager 1 and Voyager 2 are so far away now that the light leaving them takes more than 20 hours to reach us, and yet each one still pushes a few dozen watts into their little antennas. That feeble power, less than a household light bulb, is enough for our big dishes on Earth to catch and decode. Set beside that, 3IATLAS is practically on the doorstep. A few 100 million kilometers is far in everyday terms, but close for an object that might have crossed between stars. At that range, even a transmitter no stronger than a mobile phone could, in principle, be picked up by our more sensitive radio telescopes if it is using anything like the same kind of technology. And if it is willing to be heard, because of that, some of the people who spend their days listening for distant technology turned their ears, for a while, away from the stars and toward this one moving point of light. SETI, the long, slow search for extraterrestrial intelligence, usually stares at distant suns, hoping to catch a beacon aimed broadly at the galaxy, or a spill of radio noise from an alien civilization going about its business. 3IATLAS is different. It is not a star surrounded by unknown planets. It is a thing, close by, passing through, potentially artificial, and visible to us in real time. On November 5th, the Meerkat radio array in South Africa spent hours listening in its direction. Meerkat, is one of the most sensitive radio instruments on Earth. 64 dishes spread across the Karoo, linked together so that electronically they behave like a single, very sharp ear. For this observation, it listened in a band from about 900 to 1,670 megahertz, the same general range we use for many of our own communications, mobile phones, GPS links, bits of satellite traffic. If 3IATLAS were using a system at all similar to ours, that's one of the first places you'd look. While the dishes tracked the comet, a special system on the back end quietly sifted the incoming data for anything that might be a techno-signature, a narrow, organized signal that stood out from the usual hiss. Over those few hours, it flagged 23,689 candidates. On the surface, that sounds almost thrilling, as though the comet were singing to us in 1,000 voices at once. But radio telescopes live under a sky thick with our own noise. Satellites cross the beam. Aircraft and ships ping radar. Ground-based transmitters leak into the far field. When the team tested those 23,000-odd signals against one simple question, do they move with the comet, every one of them failed. A real transmission from 3IATLAS would stay locked to its position on the sky, changing frequency subtly as the object's motion Doppler shifted the waves. The interference, by contrast, stayed fixed relative to Earth, sliding in and out of the field of view in ways that had nothing to do with the comet's path. In the end, Meerkat's verdict was simple and a little anticlimactic. No radio signal detected from 3IATLAS, at least not in that band. At the distance involved, the sensitivity limit worked out to roughly 0.17 watts. That means that if there were a transmitter on the object, broadcasting steadily in those frequencies with more power than a typical phone in your pocket, Meerkat should have seen it. It did not. That doesn't mean the sky is empty of technology. It doesn't even mean that 3IATLAS is mute. It only tells us that, in that particular slice of the spectrum, during those particular hours, no obvious phone-level or stronger signal was aimed in our direction. Radio waves cover an enormous stretch of possible frequencies, slow electric ripples from a few cycles per second up to billions of cycles per second, and beyond them lie microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. The band Meerkat explored that night is a thin sliver, a single window in a wall of many panes. Failing to see something through that one glass is a little like dipping a cup into the ocean, finding no fish inside, and trying to say something very general about the sea. Even so, the result is useful. It quietly removes one simple picture from the table. If 3IATLAS is artificial, it is not broadcasting in the same kind of open, unshielded radio we tend to favor for close-range work. For a more mature technology, that might be exactly what you would expect. Radio is easy, but it spreads. A radio beam fans out as it travels, its strength dropping with the square of distance. To send a high-bandwidth signal across light years, you either need enormous power or very large, very precise dishes on both ends. Lasers, by contrast, can be focused into a much tighter beam. They lose very little intensity over distance if they are well collimated and aimed. Even we, in our technological adolescence, are beginning to experiment with laser communication between Earth and spacecraft, trading broad, wasteful radio broadcasts for narrow pulses of light. If someone elsewhere in the galaxy has been solving these problems for much longer than we have, they may have left radio behind almost entirely for serious communication. And if 3IATLAS is using tight laser beams to whisper home, we will only notice by sheer luck if one of those beams happens to cross Earth or one of our instruments. A narrow, invisible thread of light, could pass a few million kilometers from our planet, and we would be none the wiser. Instead of chasing beams, another way to look for technology is to search for heat. Any machine that uses energy sheds some of it as waste. That warmth leaks into space as infrared radiation, a ghostly glow that sensitive detectors can see. A natural comet should be only as warm as sunlight, and its own slow cooling allow. A comet with an internal power source, even a modest one, might run hotter or have parts that do. The James Webb Space Telescope is exquisitely tuned to this kind of light. It can pick out tiny changes in temperature, see faint, cold objects at the edge of the observable universe, and disentangle the fingerprints of different molecules in the atmospheres of exoplanets. On August 6th, Webb turned its gaze briefly to 3IATLAS, long before perihelion. When the comet was still far from the Sun and relatively calm, its instruments read the spectrum of the coma and found nothing exotic. Lines from carbon dioxide, water, carbon monoxide, carbonyl sulfide, exactly the roster of gases you would expect to boil off a natural icy nucleus as it begins to warm. The thermal signature matched a body being gently heated from outside, not one lit from within. No hidden reactor announced itself. No extra warmth betrayed a buried machine. That observation is soothing if your heart leans toward a natural explanation. It is less satisfying if you were hoping for a clear techno signature, but even there, the details matter. August is not October. 3 months before perihelion, 3IATLAS had not yet been pushed to the same extremes. If there is any internal system that only wakes up under stress, or only operates during particular phases of the orbit, it could easily have slept through that early visit from Webb's mirror. To know what it was doing during the truly active period, we would need infrared observations from late October and early November data that, if they exist, have not yet fully surfaced in the public domain. So far, then, the sky has offered us silence where we might have hoped to hear a voice, and ordinary ice signatures where we might have hoped to see the glow of machinery. That pattern is exactly what you would expect if 3IATLAS is a comet. It is also exactly what you would expect if it is an extremely cautious probe designed to blend seamlessly into the background. If you were sending an instrument into someone else's planetary system and preferred not to alarm the locals, you would probably choose similar strategies. You would rely on passive sensing cameras, spectrometers, magnetometers that simply watch and measure. You would store your findings on board, transmitting them only when you are far from anything that might listen, in directions and bands carefully chosen to be hard to intercept. You would minimize heat and radio leakage. You would do everything you could to be just another cold stone, glowing only with borrowed light. From the outside, those two stories, natural comet and stealthy scout, can look eerily alike. The absence of evidence becomes a void both sides can pour their narratives into. For scientists trying to stay firmly planted, that is one of the most frustrating aspects of this whole episode. You cannot prove a negative. You can only keep tightening the net until one picture or the other becomes implausible. To help keep his own thinking disciplined, Loeb sketches out a simple mental scale for interstellar visitors, running from 0 to 10. 0 is reserved for objects that clearly behave like ordinary rocks or snowballs, with no lingering oddities. 10 is the hypothetical end of the line, something whose artificial nature is undeniable and whose intent may even be threatening. Most things we see, from Oumuamua to Borisov, sit down near the base of that ladder, quiet, natural, odd in places, but not demanding anything beyond the physics we know. On that scale, he places 3IATLAS at around a 4. Not harmlessly ordinary, not wildly alarming, but in a kind of gray middle. Multiple unexplained features, but no single decisive techno-signature. In that position, the only honest response is curiosity. It is too strange to ignore and too ambiguous to label. To move it higher, to push it toward a 5 or 6 or beyond, would require direct evidence that some part of it is behaving in a way we have never seen matter behave on its own. A tight, narrow-band radio signal that tracks its motion, a laser flash with a pattern that could not arise from natural flares, an infrared glow inconsistent with sunlight and simple cooling, or the most theatrical possibility of all, those sideways jets turning out to be the visible trails of many small craft, each one holding a steady course and speed that natural fragments could not maintain. Any one of those would change the conversation overnight, but none of them will appear in our hands by themselves. They all require targeted, careful observation, while 3IATLAS is still in reach. That is why so many eyes are drifting toward one date in particular. There is a small circle on the calendar, not so far ahead, December 19th, 2025. The day when this visitor and our planet will be as close to each other as they are going to get, about 269 million kilometers apart. In cosmic terms, it's not an intimate meeting. Many comets and asteroids sweep far nearer, but distance is not just about drama. It is about what we can see. The brightness of an object falls off with the square of the distance. Step back a little, and its light thins quickly. From late November to December 19th, 3IATLAS will shave roughly 20% off its separation from Earth, and that modest narrowing will make it appear nearly half again as bright as it does now. For instruments working at the edge of their sensitivity, that extra light is the difference between guessing at a feature and tracing it clearly. Angular size matters too. At closest approach, the coma and any extended jets will span a slightly larger patch of the sky, giving high-resolution telescopes more detail to work with. Hubble's sharp eye will be able to probe the inner structure of the coma more deeply, searching for hints of hidden fragments or compact companions. Large ground-based telescopes, equipped with adaptive optics to study Earth's shimmering atmosphere, will be able to push a little closer to the limit of what they can resolve. Spectrographs on Webb and on observatories here at home may tease out finer patterns in the gas, subtle shifts that speak of unusual speeds, unexpected compositions, or quiet normalcy. It is, in many ways, a last, polite chance. After that date, 3IATLAS will keep moving outward, its activity slowly decreasing, its jets fading into thinner and thinner light. The questions wrapped around it will not vanish, but our ability to ask them with instruments rather than imagination will shrink. Between now and then, there is just this narrow band of nights, long enough, perhaps, for the right proposals to be approved, for schedules to bend, for dishes and mirrors to turn, not long enough to waste. Somewhere, in that small stretch of time and distance, lies the possibility of a clearer answer, a quiet confirmation that this was, in the end, a wild but natural wanderer, or the first unambiguous sign that the dark between the stars has been, for longer than we knew, quietly watching back. If 3IATLAS carries structure with it, if there are little companions drifting nearby, or if those strange jets are woven from finer patterns we can't yet see, then every bit of distance we close makes the hidden details a little less hidden. Hubble, for all its sharpness, is still bound by the wave nature of light. There's a limit to how small a feature it can distinguish at a given distance. From a few 100 million kilometers away, it can't pick out a tiny probe the size of a town, but it can start to sense when the light isn't coming from a single, smooth glow, when the inner coma is clumpy instead of uniform, when brightness gathers in knots, when lines in the jets look more like stitched threads than blurred brushstrokes. At closest approach, that subtle texture becomes easier to feel. And then there is the color of the light itself, not just what our eyes would see, but the full spectrum, stretched and combed apart. Spectroscopy is how we learn what something is made of, how warm it is, and how fast it's moving. Each atom and molecule leaves a signature: thin, dark lines where it absorbs, thin, bright lines where it emits. The more photons you collect, the sharper those signatures become. At December's closest pass, 3IATLAS will be as generous with its photons as it's going to be. That's when instruments like Webb can do their quietest, finest work. With a large mirror and sensitive detectors, Webb can do more than just say there is water or there is carbon dioxide. It can measure how those lines shift with the motion of the gas, revealing velocities through Doppler shifts, tiny nudges in wavelength that tell you whether the gas is coming toward you or flowing away, and how fast. It can read line widths that hint at temperature, see how strong or weak certain features are, and from that, infer density. All of that wrapped together is what we really need to disentangle the story. If the gas in those jets is drifting out at a few 100 meters per second, at temperatures that make sense for ice warmed by the sun, and if its composition is the usual mix: water, carbon dioxide, carbon monoxide, a few familiar companions, then the case for a natural explanation grows softer and steadier. Odd, yes. Unusually energetic, yes, but still within the long reach of what ice and sunlight can manage. If, instead, the lines whisper something else, a flow of several kilometers per second, temperatures too high for ordinary solar heating, unexpected elements or compounds that don't sit comfortably in the catalog of comet chemistry, then the ground shifts. It wouldn't instantly prove technology, but it would force us to admit that something more than simple sublimation is at work. Loeb has been saying this, gently but insistently, in every way he can. In essays, in interviews, in long conversations that drift late into the night, his refrain is simple: this is the moment to look. Not someday, not after the fact, now. While the object is near enough and active enough that our best instruments can still catch it in the act, 3 years from now, 3IATLAS will be a memory and a trail of numbers. The chance to see the fine print in its behavior is not renewable. Beyond Jupiter, in March 2026, it will be moving out into the quieter dark, receding at 60 kilometers per second. Its activity dwindling, its signal thinning beyond what even our sharpest telescopes can resolve. After that, it will be just another faint visitor in our databases, racing back into the interstellar gulf. Whatever we didn't learn by then, we likely won't ever learn. Against that ticking clock stands something more mundane and more stubborn than any comet: the way we allocate attention and resources. Time on Hubble and Webb is scarce. Hundreds of proposals ask for a slice of night, each with its own promise and urgency. Committees weigh them, looking for projects that are likely to bear solid fruit, clear data, clear conclusions, work that can be written up and folded neatly into what we already know, or gently extend it. From that vantage point, devoting precious hours to chase the faint possibility that 3IATLAS might be artificial feels, to many, like a long shot. Most astronomers working directly on it believe it's natural, albeit strange. For each anomaly, they can sketch a path back to unusual but still natural processes. If the odds of "it's just a comet," if an extreme one, feel high, and the odds of "it's a machine" feel very, very low, then it's easy to see tuning the instruments elsewhere as the sensible, responsible choice. Loeb looks at the same ledger and sees a different kind of arithmetic. Even if the chance of an artificial origin is only 1%, or a tenth of that, the value of catching such a thing, of confirming that someone else has left fingerprints in our sky, is so enormous that multiplying those small odds by that huge payoff still yields something you can't in good conscience set aside. To him, ignoring that possibility is like turning away from a lottery ticket already in your hand, unopened, because you assume it must be a loser. We've lived through a version of that before. When Oumuamua slipped through the inner solar system in 2017, we saw it late. It was already on its way out by the time we realized how peculiar it was. We measured its path, puzzled over its shape, argued about the lack of a visible coma, noted the slight but persistent non-gravitational acceleration, and then watched it fade beyond the reach of our best eyes. Now we have only models and memories, and the debates about what it was, shard of rock, exotic comet, fragment of a larger body, light sail, will likely never be fully settled. With 3IATLAS, we arrived earlier to the story. We've followed it in from the outskirts, watched it brighten, seen its jets blossom and twist. Spacecraft have caught glimpses from different angles. Webb and Hubble have already had their first looks. Amateur astronomers have filled in dark gaps with their patient exposures. We are, in many ways, better positioned now than we were with Oumuamua. Yet there is still a sense of hesitation, as if we are waiting for someone to hand us definitive proof before we decide it is worth committing our very best tools. The danger in that is simple. Decisive proof might only show itself because we point those tools. If we wait for certainty before taking a closer look, we might never get either. So the quiet question hanging over December 19th is not just what will we see, but what will we be brave enough to ask for? If the observing time materializes, if Hubble, Webb, and the big ground-based telescopes all spend those nights staring into this moving patch of sky, then the possibilities unfold in three broad directions. One is calm and simple. The spectra come back with familiar fingerprints: water, carbon dioxide, carbon monoxide, maybe a few minor species, at temperatures and speeds that fit neatly into the physics of sublimation. The images show a bright, turbulent coma with jets and arcs and filaments, but no obvious knots, no separate bodies slipping away on their own straight courses. The jets look wild, but ultimately tethered to solar heating. Complex, perhaps, but not inexplicable. In that case, 3IATLAS would settle slowly into the category of strange but natural. We would update our models of interstellar comets, widen the range of what we think they can do, and move on a little wiser. Another possibility is sharper. Somewhere in the data, lines are shifted in a way that implies gas racing out at several kilometers per second. Temperatures are higher than sunlight alone can justify. Elements appear that have no business in an ordinary comet. Hubble's images hint at small, dense knots, moving apart along straight, persistent paths, like beads sliding down invisible wires. Webb picks up an infrared glow suggestive of internal power that does not switch off when it should. One or two such clues could be argued away, but many, lining up together, would point strongly towards something we do not yet see in nature. That would push 3IATLAS higher up Loeb's internal scale, nudging it closer to the territory where artificial is no longer just a provocative word, but a serious working hypothesis. The third outcome sits between those two and, in some ways, is the most uncomfortable. We might see enough to know that the object is not behaving simply, but not enough to cleanly separate natural from artificial. Velocities that are high, but not impossibly so. Structures that are suggestive, but not conclusive. Chemical signatures that are unusual, but could just be the fingerprints of an interstellar birthplace we haven't encountered before. In that murky middle, every new piece of evidence becomes a Rorschach blot, one that different minds will read in different ways. In that scenario, the arguments will stretch on, papers will appear and be answered, conferences will hold long, careful sessions. Some scientists will lean heavily on the side of extreme natural behavior. Others will keep the technological door ajar. Outside the journals, the public conversation will swing between fascination and suspicion, between trust and the feeling that something important is being softened or delayed. The last few months have already bent that trust. The government shutdown that choked the flow of information just as 3IATLAS was at its most interesting. The late release of key images, the cautious phrasing at the November press conference, all of these have fed a certain narrative that perhaps there is more known than is being said, that the truth, if fully stated, would be too unsettling. Whether that perception is fair or not, it lingers. December 19th will be a test of more than just optics and spectra. It will be a test of openness, of whether the institutions that watch the sky for us can show plainly what they see, even when what they see is strange. If, in the end, 3IATLAS turns out to be a natural comet, even an extraordinarily odd one, then the universe will have simply reminded us how small our sample still is, how easily we mistake first time we've seen it for cannot happen. If, against the odds, it turns out to carry evidence of design, then we will find ourselves slowly adjusting to a new kind of night, one where the dark between the stars is not entirely empty of intention. Either way, the path forward runs through the same narrow gate, data, carefully taken and honestly shared. That, in the quiet, is what this all comes back to. Not an announcement at a podium, not a sudden dramatic revelation, but a stack of observations, spectra that tell us how fast the gas is moving and how hot it is, images that hint at structure or smoothness, infrared measurements that whisper how much warmth lies within. From those, we can build, slowly and calmly, the best picture we can of what 3IATLAS truly is. For now, the only honest promise we can make to ourselves is simple. Look at what the sky is showing us, follow the trail as far as it will go, and be ready to accept the answer even if it leaves us feeling smaller or stranger than we expected. Just as that thought was settling, something new stepped onto the stage. On November 2nd, only a few days after 3IATLAS passed closest to the Sun, astronomer Gennady Borisov reported a fresh object in the inner solar system. Borisov is the same observer who discovered 2I. Borisov, the second confirmed interstellar visitor back in 2019. This new arrival is catalogued as C 2025 V1, or simply V1. And from the beginning it carried the faint sense of being entangled with our current mystery. V1 moves on a steeply tilted path. Its orbital plane is inclined by about 113 degrees relative to the flat disk where the planets circle. That means it's diving through the solar system from above, almost perpendicular to the planetary plane. That's unusual, but not shocking. Comets that fall in from the distant Oort cloud, a vast, roughly spherical shell of icy bodies, far beyond the planets, often have orbits like this, tipped at all sorts of angles. The more delicate question is whether V1 is bound to the Sun at all. Its measured eccentricity, the number that tells you how stretched its orbit is, sits around 1.95, but with a large uncertainty. Values above 1 usually mean a one-time, hyperbolic flyby, in once, out forever, like 3IATLAS. Values just below 1 mean a long, thin ellipse, an object looping slowly in from the Oort cloud and someday back out again. With the current errors, V1 could, in principle, fall on either side of that line. To untangle that, you can take the best fit orbit and run it backward, letting it drift out to about 1,000 astronomical units from the Sunday. That's far enough that the planet's tugs become tiny, and you can see what the orbit looked like before their influence mattered much. Do that, and in Loeb's calculation, the eccentricity dips below 1. In other words, V1 behaves like a comet that has long been loosely bound to the Sun, probably a member of the Oort cloud, not a second interstellar interloper. On paper, that makes V1 one of ours. In practice, its timing and its path still tug at the mind. It was discovered just after 3IATLAS reached perihelion, and although their orbital planes are very different, the track V1 follows passes relatively near where 3IATLAS was in October. The closest approach between their paths is about 75 million kilometers. In human terms, that's huge. In a system where distances are routinely counted in billions of kilometers, it's unexpectedly close. That nearness has led Loeb to quietly ask whether V1 could somehow be connected to 3IATLAS. Could it be a piece that's separated? A small body that left the main object and is now moving independently, under pure gravity, and the gentle pushes we've measured from 3IATLAS's outgassing? The answer seems to be no. The comet's non-gravitational acceleration is too small to throw a fragment onto V1's current track. Without some extra push, the two objects were never in the right place at the right time to trade pieces. To bridge that gap, you would have to imagine V1 receiving its own thrust after departure, some way of steering that doesn't come from sunlight alone. If that were true, it would be a sign of something very different from an ordinary chunk of ice. Complicating things further, V1 doesn't yet look like a typical comet. Early images show it as a simple point of light, with no obvious fuzzy coma and no tail, even though it's close enough to the Sun that ordinary ices would usually begin to boil off. That doesn't prove anything, but it nudges us into an uncomfortable corner. If V1 is a dormant comet, it might be sheathed in a dusty crust that keeps its interior ices from venting. If it's an asteroid, mostly rock, its apparent Oort cloud origin becomes harder to explain because that distant reservoir is thought to be largely icy. So three possibilities sit quietly, side by side. V1 could be a sleepy Oort cloud comet whose surface is sealed. It could be a rare asteroid kicked out to great distances in the past and now falling back in. Or it could be a piece that left 3IATLAS, with our orbit models missing the non-gravitational forces that shaped its path after separation. Loeb isn't insisting on that last option. He's simply saying that the coincidence in time and place is suggestive enough that we shouldn't dismiss it without taking a closer look. The way to move from suggestion to clarity is the same as always: better observations. Sharper images can reveal whether V1 has even a faint coma, whether its light flickers in a way that gives clues to its rotation and shape. Spectra can tell us what it's made of. If it turns out to be a normal, dormant comet or a small asteroid, the idea of a connection to 3IATLAS fades. If it begins to show similar anomalies, odd activity, strange jets, unusual chemistry, the two stories start to rhyme. Meanwhile, 3IATLAS itself continues to show a layered complexity. Recent high-quality images reveal not just one or two outflows, but a whole bouquet of them. In one November frame, observers counted at least 7 distinct jets, some aimed roughly toward the sun, some away, others leaning off at diagonal angles that don't line up cleanly with the simple picture of ice gently boiling in sunlight. If each of those jets traces a path along which not only gas and dust, but larger pieces might move, the idea of many objects gains a bit more footing. Loeb has estimated that, based on the measured non-gravitational acceleration, something like 10 to 20% of 3IATLAS's mass could have been shed near perihelion. If that loss included large fragments or dense probes weighing millions of tons each, it wouldn't be surprising to find dozens of discrete bodies spreading out along different lines. Most would be too faint or too small to see from Earth, but a few of the bigger ones, or those whose paths happen to bring them into favorable positions against the background stars, could be within reach if we deliberately search the space around the comet instead of only staring at its core. That is one more reason December 19th matters so much. At closest approach, we have a chance not just to examine the nucleus and the inner jets, but also to survey the region around it. Wide-field telescopes, the kind that can capture large patches of sky in a single exposure, could map the area within a few million kilometers of 3IATLAS, looking for faint dots that share its general motion but follow slightly offset tracks. Once found, those dots could be followed night after night, their orbits refined. If they coast along exactly as passive fragments should, their paths shaped only by gravity, sunlight, and a little outgassing of their own, then they are probably just debris. If any of them maintain unusually stable separations, or seem to drift in ways that hint at controlled adjustments, the conversation changes. All of this deep imaging of V1, wide-field searches around 3IATLAS, careful spectroscopy and timing, takes time, money, and coordination. It requires people who manage telescopes and grants to agree that this is more than a curiosity. Many are not convinced. From their point of view, 3IATLAS can still be read as a natural, if extreme, comet. V1 can still be filed under odd but explainable Oort cloud bodies. Linking them and invoking probes or fragments with propulsion feels to them like building towers on sand. Maybe they are right. The universe is busy and coincidences happen. A strange comet and a steep orbit visitor appearing at the same time may simply be two unrelated stories overlapping by chance. But it's also true that science has advanced again and again because someone refused to gloss over things that didn't quite fit, because they were willing to say, gently, something here doesn't match our expectations. Perhaps the expectations need to move. Ideas like drifting continents, invisible black holes, and an accelerating universe were all uncomfortable once. Loeb, in his way, is playing that same role now. He is not waving his hands in the dark. He is taking the available data and pushing it to its logical edges, including edges that lead toward possibilities we haven't allowed ourselves to take seriously. For that, he has become a target of criticism, labeled sensational, accused of courting attention. But controversy alone doesn't make a calculation wrong. It only marks that the conclusion sits outside our comfort zone. Whether you find his arguments persuasive or not, the sky's behavior is still there to be explained. We have 3IATLAS with its crowded list of anomalies. We have V1 arriving on a steep, oddly quiet path at just this moment. We have a narrow window of time when we can still ask the universe, with instruments instead of guesses, what exactly is passing through our neighborhood. If there is even a small chance that these pieces belong to some larger pattern, then the gentle obligation that follows is clear. We have to look with everything we have while we still can. 3IATLAS is already on its way out. Night by night, it slides a little farther from the sun, a little fainter in our telescopes, a little harder to study in detail. By the time January settles in, the best windows for the sharpest observations will have passed. By March, as it brushes past Jupiter's orbit, it will be more memory than presence. And a little after that, sometime in 2026, it will simply be gone back into the deep, carrying its secrets with it. We have not had many chances like this. In all of human history, we have confirmed only 3 visitors from beyond our own planetary family: Oumuamua, 2I, Borisov, and now 3IATLAS. The next one could arrive in a decade or in a century. There is no schedule on the wall, no guarantee that another will come when our instruments and attention are ready. For all we know, this is the only close brush with an interstellar object that any of us will see in our lifetimes. That is why the calendar suddenly feels heavy. Those sideways jets first appeared in the image from November 20th. The date circled ahead. December 19th is the moment of closest approach to Earth. Between those 2 markers lies only a narrow strip of time. In those days, if the many objects are real, they continue to drift farther from the main body, tracing another 1,000,000 kilometers or more. In those days, observers decide whether to turn their lenses toward this visitor or toward other, quieter targets already on the schedule. In those days, data can be gathered, shared, puzzled over, or allowed to slip away. From the outside, 3 weeks feels like a long time. Inside professional astronomy, it is barely a breath. Time on the great telescopes is usually planned months or years in advance. Proposals written and refined, arguments weighed by committees, schedules laid out like intricate tapestries. You cannot simply whisper to Hubble or Webb and have them turn their gaze next Tuesday. To bump other projects aside, you need an extraordinary case, and you have to make it to people whose job, in part, is to guard against chasing every glimmer that looks unusual. Loeb has been trying to make that case. He has written, argued, presented, pointing to the 12 anomalies, to the X-shaped jet, to the stubborn anti-tail, to the possibility that large fragments or probes have fanned out along those strange directions. He is not alone, but he is more vocal than most. And the response he keeps meeting is a kind of careful, polite hesitation. Not a hard no, but a soft, let's see, which in a time-sensitive situation can be just as final. By the time committees finish their deliberations, by the time schedules flex, the object may already be too far for the most revealing measurements. None of this is a dark plot. It is simply how a system, built to be cautious, behaves when confronted with something that sits outside its comfort zone. Resources are limited. Most scientists see the odds of an artificial explanation as very small, and the odds of an extreme but natural comet as much higher. From that angle, tilting the machinery toward low probability possibilities feels irresponsible. But probability is a slippery thing in a universe that keeps surprising us. Before we saw 3IATLAS, what were the odds that an interstellar comet would show an X-shaped jet, a persistent sunward tail, sideways structures that ignore the usual rules, and a whole catalog of other oddities? If we had tried to assign a number to that exact combination beforehand, it would have been essentially zero. And yet, here it is, shining quietly in our sky. The lesson is not that anything goes, but that our intuition about what is likely is shaped by a very small sample. We have seen only a handful of interstellar objects. We do not yet know what typical looks like. In that situation, being too quick to dismiss strange behavior because it sounds unlikely can be as misleading as believing every wild story you hear. The tools we need are not exotic. Measuring jet velocities with spectroscopy is something we know how to do. Imaging the inner coma at high resolution is well within the reach of existing telescopes. Searching the region around the comet for faint companions is exactly what wide-field surveys do when they hunt for asteroids every clear night. None of this requires new technology. It requires the will to point familiar instruments at a target that makes some people uneasy. There is a slogan in science that extraordinary claims demand extraordinary evidence. It is true, but extraordinary evidence does not appear on its own. Someone has to make the observations that could, in principle, reveal it. If we never dare to look closely at the strange things, we quietly guarantee that our evidence will always be ordinary. Right now, what we have is suggestive rather than decisive. Odd patterns, improbable alignments, behaviors that strain our standard models. They raise the possibility that 3IATLAS is more than a normal comet, but they do not prove it. To move beyond that fog, we need the kind of concentrated, coordinated effort that we usually reserve for safer, more conventional targets. We need, for a brief span of nights, to treat this visitor as if the answer really matters. How we handle that matters for more than the numbers on a page. It matters for trust. If the observations are sparse, scattered, and slow to appear, people will fill the gaps with their own narratives. If the data is gathered but held back for long, analyzed behind closed doors while rumors churn outside, suspicion will grow in the quiet spaces between official statements. We have seen that already. The shutdown silence, the late release of key images, the careful phrasing at the November briefing, all of it has fed a sense that perhaps there is more known than has been said. The antidote is not to promise certainty where none exists. It is to be as open as possible about what we are doing and what we are seeing, releasing data quickly, letting many teams check it, argue over it, and publish their own interpretations in the light rather than the shadows, does not eliminate confusion, but it shifts it into the realm of shared inquiry rather than whispered suspicion. Imperfect transparency is still far better than a polished void. Loeb, for all the controversy around him, has chosen to work in that open way. He posts his calculations, walks through his reasoning, invites criticism. That has made him a target, but it has also allowed anyone who wishes to follow the thread themselves, step by step, instead of taking his word for it. In some sense, he is modeling the uncomfortable side of scientific honesty, the willingness to be wrong in public, to risk reputation in order to test an idea that might, just might, reveal something profound. On the other side of this approaching moment lie only a few broad possibilities. The data we gather around December 19th may show that 3IATLAS is, in the end, a comet, an extreme one, rich with new lessons about interstellar ice and the violence of close solar encounters, but still a natural child of distant cold. Or the data may whisper something we can't easily file away. Jets moving faster than they should, fragments traveling in ways gravity alone cannot explain, temperatures too high for simple sunlight, structures too regular to ignore. It is also entirely possible that what we see will sit somewhere between those two poles, ambiguous, messy, rich enough to fuel arguments, but not clean enough to settle them. In that case, the story stretches on. The comet fades. The papers appear. The debates continue in conference halls and quiet offices. The public, watching from further away, may find it hard to know what to believe. Underneath all of that, though, is a quieter truth. Whatever 3IATLAS turns out to be, our feelings about it, our hopes for contact, our fears of being observed, our wish to stay alone, our longing to belong to a larger story, do not change its nature. The universe does not bend itself to our comfort. It simply is. Our task, if we care to take it up, is not to make reality match our desires, but to look closely enough that we can see what is actually there. For some, the idea that 3IATLAS might be artificial is thrilling, a sign that someone else has climbed the same ladder of curiosity, built machines, and cast them into the dark to ask their own questions. For others, that idea is unsettling, even frightening. The thought that our small system might be under watch, that our existence might already be in someone else's catalog, changes the feeling of the night. Both reactions are human, both are understandable, but neither should determine where we point a telescope. In the coming nights and weeks, instruments will turn, data will flow, and the first analyses will begin to take shape. The numbers won't give us everything, not all at once, but they will move us closer. Velocities traced in spectral lines, temperatures inferred from faint colors, hints of structure in the blurred glow around a tiny, distant point. That is how science advances, not in single, blinding revelations, but in steady steps, each one leaning on the last. One observation, one calculation, one revised model at a time. The fog thins. When we look back years from now, 3IATLAS will be one of those steps, a strange, luminous mark on the path. Perhaps we will remember it as the comet that forced us to expand our sense of what ice and rock can do between the stars. Perhaps we will remember it as the first clear sign that we are not alone. Either way, it has already reminded us of something easy to forget, that the universe is not obliged to match our expectations. It is wider, wilder, and more intricate than the stories we tell about it. Our theories are sketches on the surface of something deep. Every anomaly is not an embarrassment, but an invitation to learn more, to refine our models, to listen more carefully to what the cosmos is trying to say. So for now, we wait and watch, together under the same sky. The days will pass, the comet will move on, and the data will arrive. Not all the answers, but more than we had before. And in that more, in each small improvement in our understanding, there is a quiet kind of grace, the feeling that, even in the vast dark, we are capable of noticing, of asking, and of inching, little by little, toward the truth.